some sample problems. And to do that, we're going to set up a special type of table that you're going to learn to know and love in this class. It is called a Rice table, R-I-C-E, which stands for reaction, initial, change, equilibrium. Okay, so let's see how that goes. So here's our problem. Carbon monoxide reacts with steam to produce carbon dioxide and hydrogen. At 700 K, the equilibrium constant is 5.10. Calculate the equilibrium concentrations of all species if 1 mole of each is mixed in a 1-liter flask. Okay, let's unpack this thing. So at 700 K, that's not so important, but what is important is the value of the equilibrium constant. Okay. Another piece of information that's important, 1 mole of each is mixed in a 1-liter flask. Okay, so that's all the quantitative information we need. And so now let's follow this procedure of making a Rice table. So the R stands for reaction. So the first thing we got to get is a reaction. So this says carbon monoxide reacts. So that's carbon monoxide, and that's a gas. Reacts with steam. So that's H2O gas to produce. So that means in equilibrium to produce carbon dioxide. Okay, good. That's a gas. And hydrogen. And specifically, this has to be H2. Okay, not H plus. It's got to be H2 based on that this is all gas phase reaction. Okay, great. So now we got this little table going here. And I'm going to separate it all out. I'm going to put a line under all of the reaction. And I'm going to get myself a little grid going here. Okay, perfect. And so now what I'm ready for is the I, which is initial. So I need to get the initial concentrations of everything. And it says if all species, 1 mole of each is mixed in a 1-liter flask. So 1 mole in a 1-liter flask means 1 molar. Okay, and it says of all of them. So that means that's 1.000 molar, 1.00 molar, 1.00 molar, and 1.00 molar. Okay, great. So we got the I part. Okay, now we need the C, which is the change. And so we're going to calculate the change by calculating Q, by calculating the reaction quotient. Okay, so we know that I'm going to do that up here. I'll write the reaction quotient. So that's going to be products divided by reactants. So that's going to be CO2 times H2, all divided by CO times H2O, right? So it's the same procedure as getting the equilibrium expression, but we use the initial concentrations instead of the equilibrium concentrations. So now let's plug all those values in. So it's going to be real simple. 1 times 1 divided by 1 times 1 equals 1. So here we can see K was equal to 5.10, but my Q is equal to 1. So that's a Q less than K. And let's remind ourselves of what that means. If Q is less than K, the reaction as written proceeds in the forward direction. So let's look at our other cheater notes here. Okay, so if Q is less than K and it has to shift to the right, that means minus X for reactants and plus X for products. Okay, so let's get back into that. So now we know the change. All we're going to do is put what we're doing. So here, that's going to be minus X. This one's going to be minus X. This one's going to be plus X. And this one's going to be plus X. And let's see, I need to extend my grid just a little bit. And we're ready for the last column, which is E. And that stands for equilibrium. Okay? And so to get the equilibrium, we just add together the initial to the change. We just bring it all down. And so that means this is 1.000 minus X. I'm going to keep all of those sig figs in here because when I'm doing the algebra, it's important to keep track of those significant digits, okay? And so now the CO2 is 1.000 plus X, and the H2 is 1.000 plus X. Okay, so now we've got our rice table is all set up. And so we can plug everything into the equilibrium expression. Okay, and we can do that by saying K equals, and we know that K is 5.10 is given to us right there. Okay, and so once again, we know it's CO2 times H2 on the top. So that's going to be 1.000 plus X. And I'm just going to write it all out for completion. Okay, so because we know really that's 1.00 plus X all squared, right? But we'll just write it out to be complete. And we know that now that is divided by carbon monoxide times H2O, which is 1.00 minus X for each. Okay, 1.000 minus X. So now we're just going to do the same thing we did last time and solve for X. However, before you guys start singing your favorite new song that I taught you, quadratic equation, take some time and just think about this for a minute. Does this even need the quadratic equation? Okay, not all problems do. So let's simplify this and see what we can make of it. So this becomes 1.00 plus X all squared divided by 1.00 minus X all squared. Okay. And so now what I can do here is I can take the square root of this side to get rid of those squares. And if I take the square root of this side, then that means I also take the square root of that side. Okay. So let's simplify this. So now that's 5.10 square root. So with the three significant digits, that's 2.26 equals. And then now I square root of this whole thing. That's just going to become 1.00 plus X, all divided by 1.00 minus X. And then now we can just rearrange algebraically and solve for X. So I'm going to multiply everything on the bottom over to the other side. So that's 2.26 times 1.00 minus X, all equals 1.000 plus X. I know it's a pain in the butt to keep all those sig figs, but we need them there for our final answer. Okay. So now continuing along, we'll push this up here. So when I multiply through this 2.26, okay, look, I got 3 sig figs times 4 sig figs. The 3 sig figs is going to win, right? So that becomes 2.26 minus 2.26x. And then so I multiplied that through. And then now what I'm also, or let's just go ahead and, sorry, we'll just keep that all together so that we can keep it straight. So now I'm going to subtract the 1 over to here, and I'm going to add the 2.26x over to here. So when I subtract that 1 over, I get 1.26 equals, and then now I'm going to add that over. And so 2.26x plus x equals 3.26x. Okay. And then now I can just divide both sides by 3.26, and x equals 1.26 divided by 3.26. And so you can see that was really straightforward. I didn't need any quadratic equation or anything. So we do need to take our time and think about the algebra, right? Okay, so now x equals, and then 3 sig figs. So that's why I just kept my significant digits the whole way through, so I get it right. So with 3 significant digits, this is 0.387. Okay. And so now we're not done yet because we've got to get the equilibrium concentrations. Okay. So, and what we do to get the equilibrium concentrations, we plug our value of x back into everything in this column right here. Okay. So that means now my final answers, okay, CO equals H2O, which equals, so that's 1.000 minus 0.387. I can do that in my head. That's 0.613 molar. And then we've got CO2, which equals the H2 concentration as well, Okay, and so that was 0.387 plus 1.00, so that is 1.387 molar. And I'm going to box these off. These are our final answers. But if we wanted to check that these are correct, then what we can do is plug those concentrations back into our equilibrium expression. So I'm just going to do that on my calculator directly here. So we know CO2 and H2 is 1.387. So that's 1.387 squared, okay? 1.387 squared. And then now that's going to be divided by 0.613 squared. So 0.613 squared equals, and then look at that. I got not quite 5.10, I got 5.12. That's fine. That's perfectly fine. So perhaps if we had carried a few extra sig figs through, we would have got that 5.10 right on the money. However, we want to follow the sig fig rules, okay? So it's totally fine if the concentrations we calculate give us an equilibrium constant that's, just a little bit off.